for his research and his tireless scientific involvement is Samuel Candler-Dobbs, professor at Emory, and currently Emory University, and currently mathematics department chair, and author of a large number of papers, co-author of a book on the blurring images, and of a popular Matlab package on iterative regularization methods. Jim has consistently served our community, in particular the Householder Symposium and SIAM in various positions, currently as SIAM Vice President for Programs, and is also SIAM Fellow, class of 2016. I could continue with a number of awards recognition, however, I prefer to leave Jim the lead for this talk. But let me remind you that if you wish to ask questions, please write in the chat and you will be given the opportunity to speak up at some point. So Jörg Liesen is on Zoom and Alex Townsend is on YouTube. So please, Jim, can start.
Okay, thank you, Valeria, for that really nice introduction. I want to thank Melina, Stefan, Daniel, Jörg, Valeria, Alex, and Bart for organizing this amazing set of seminars. It really is an honor to be here, I have to say. I also want to begin by saying that I'm going to apologize. Krylov subspace methods and regularization inverse problems is a very broad area, and so I apologize if I don't cite everybody's work, but that would be difficult to do in a talk like this. So let me just begin. If you don't know Atlanta by now, we've become quite popular in the news in recent weeks and months. But it's in the southeast part of the United States. So the red part is the state of Georgia, and blue is approximately where Atlanta is located. It's home to Martin Luther King and John Lewis, who are civil rights leaders, and among other people who are civil rights leaders. Jimmy Carter's Presidential Library is in Atlanta, and it's the home of the Centers for Disease Control. Actually, the CDC main campus is right next door to Emory's campus. So Emory's, let me tell a little bit about the university. We're a private university east of downtown. You can see downtown in the background there. We're in a nice residential area here. So Jimmy Carter is one of our distinguished professors since 1982. He holds a town hall with undergraduate students every year, which is quite a nice activity. We have about a relatively small university, about 7,500 undergraduate students and about 6,500 graduate students. Probably the university is most well known for its large, highly ranked medical school, including in areas of infectious disease, cancer research, and cardiology. And in fact, there are colleagues in my department that collaborate with people in cardiology, modeling blood flow, for example, and also in radiology and computational imaging. And that's pretty much the reason why I moved to Emory about 21 years ago now. So let me tell you about the aims of this talk. So I want to discuss iterative methods to solve large-scale inverse problems. So the idea here is that you're given a matrix A and vector B, and of course the goal is to compute an approximation of vector X. The trouble is that you don't know A times X exactly. You have a perturbed version of it. And also the matrix A is typically very ill-conditioned, and so this makes trying to compute approximate solutions quite challenging. So I'll begin with some introduction of basics. I need some notational background to talk about some of the more sophisticated methods in terms of Krylov subspaces. So I'll talk about standard Krylov subspaces, some hybrid methods, and about halfway through here, I'll pause for a few questions, and then I'll talk about our more recent work on using regularization to compute sparse solutions and low-rank solutions. All right, so let me begin by this most amazing operator, the backslash operator. I know you probably can't read this slide exactly, but you can go into Matlab and open your documentation on ML divide. And it's just an amazing operator, right? It does everything that you hope it would. It checks to see if matrix is square, if it's looks like it's going to be symmetric and positive definite, and it decides what algorithm to use. And it really works well. It's kind of an amazing operator. So the key is when we start talking about inverse problems is that is it possible to have a backslash operator like thing for inverse problems? Basically, the answer is no, but we try to get there by trying to provide guides for users. Okay, so let me come back to the main problem here again. So I'm given matrix A and vector B. B is a noise corrupted version of A times X. And I'd like to compute an approximation of this vector X. Typically, the noise is small compared to say what's going on with A times X, but it's not negligible. And so typically the matrix A is ill-conditioned in such a way that the large singular values typically correspond to what I would call low frequency singular vectors, vectors that don't oscillate very much. And then small singular values correspond to more high frequency singular vectors. And if you look at trying to ignore the noise and just say, well, let me just use backslash on it, and you hit it with a backslash B, you compute what we might call a naive inverse solution. And keep in mind that, again, that B is not exactly A times X, it's A times X plus some noise. So when you invert it, you get something that looks like the solution X plus some inverted noise. And because A is severely ill-conditioned, typically, this noise gets magnified. And although the solution that you're after is in there somewhere, it's typically hidden by that amplified noise. So that thing's typically not a good approximation of vector X. All right, so what can you do? Well, typically, one way to think about it, the easiest way to think about it is in terms of the singular value decomposition. So if I were to decompose A into its singular value components, I can write out the solution as a linear combination of the right singular vectors. And these are, of course, the coefficients in here. So instead of computing this thing all the way to the rank of the matrix, I can truncate it at some point and avoid dividing by the small singular values because the matrix is so ill-conditioned. And if I do that, typically you can get a pretty good solution. Now, of course, the big question is where to truncate at, and we'll talk about that in a minute. Another approach is to use something like standard Tikhonov regularization, where you would try to find a solution that is a combination of a good fit to data, minimize the fit to data, but don't let the solution blow up so much. So you put a weighting parameter on it, this alpha, and you tune that parameter that says, okay, I want a good combination of fit to data and my solution not amplifying too much. Now, this is called standard Tikhonov regularization. You can say, put something else in here, an operator times X, and I'll talk about that later. And then you're saying, I would like to not blow up whatever L times, or whatever that operator is, times X. Standard Tikhonov regularization is kind of nice because you can write it in terms of the singular value decomposition, and it looks something like this. You have the components that you would get in your inverse solution multiplied by what are called typically filter factors. And so they depend on the singular values, of course, and this parameter alpha that you have here. And so typically, as I said, alpha is chosen to balance these two terms. And if you look at it this way, it sort of balances how much you want these singular values to contribute to your solution or not. So that's been generalized, of course, and Per Christian Hansen wrote a lot of papers about this kind of stuff, where you say, okay, well, this is just some sort of function of alpha. Why not replace it with something else, which does a similar sort of thing? And the basic idea of these sort of filters is to allow good stuff through and to block bad stuff. So that is, allow the large singular components through and to not allow the small singular components through. And so there are many ways you might choose these filter functions, if you like. But I won't talk about those. I'll stick mostly with these two, TSVD and Tikhonov. Now, once you write it down in terms of the SVD, the nice thing about it is that you actually, of course, need to choose this parameter alpha. Now, my alpha could correspond to this truncation K, if you like. That we could think about it that way, phi of K, if you like. But in any case, I have a parameter that I need to choose called the regularization parameter. And the nice thing about SVD is that there are, it sort of helps you choose a guide for these regularization parameters. Now, typically when I give talks like this, I try not to call them methods that choose parameters, because that's kind of hard to do in inverse problems. They're guides. They help us choose a parameter that might be good and often are good for many problems, but you have to use them as a guide and you need to know something about your application. In any case, there are many, many, many methods. I'm just going to list two here. One is probably the two most well-known, discrepancy principle, which requires needing something, some information about your noise level. And then generalized cross-validation, which doesn't require your noise level, but uses information in the data to try to statistically find a good regularization parameter. I won't talk about these methods in detail, but I did want to mention them because we will use them in part of the talk. All right, so let me just summarize this sort of very beginning part of SVD-based methods. This is old work. There's a lot of stuff on it. Per Christian Hansen has written many, many papers on these sorts of things. They're very nice papers. He, of course, has a couple of books on it that I've cited here, published by SIAM. And then, of course, his very well-known regularization tools package that you can use to test problems for algorithms, and there are test problems and things like that. And there's a link to his codes there. All right, so of course we're talking about large scale problems, and so what we want to think about is using iterative methods for these things. It's going to be hard to compute a singular value decomposition, even if A is sparse. Typically, you need many singular values and singular vectors to get enough information to know something about your regularization parameter. So it's hard to say, well, I'll just compute 10 of them, say, but if your matrix is, you know, 1,000,000 by 1,000,000, you may need a lot more components than just 10 to figure out what's going on. So typically what people do is apply iterative methods, and you can just apply your favorite Krylov subspace method, conjugate gradient type methods, LSQR, GMRes. And typically they mimic truncated SVD if you stop the iteration, what we might call early in some sense. So don't drive the residual to 0, but drive it to a certain point and then truncate. And typically that will mimic truncated SVD type solution. You could, of course, forget about this kind of idea and just add a regularization term as we did before, a Tikhonov regularization, and then apply an iterative method to this problem, this sort of variational problem here, a fit to data term plus a regularization term. And of course, there are lots of options there then that you might choose. As I said, you can choose a standard Tikhonov regularization or put in an L matrix there. You could use total variation, L1, and so forth and so on. And we'll talk more about these things later in the talk. Again, there is this issue, though, once you do this, you have to decide how to choose this parameter alpha. Of course, up here in the truncated iterations, you have to decide when to stop your iteration as well, because you're not going to drive the residual to 10 to the minus 8, for example, typically. All right, so the sort of moral of this beginning part is that there's not one method to fit all. Hard to find a simple flow chart for choices like Backslash has for a standard linear algebra type problem. But if we can combine, so if you look back at what I talked about on SVD, there are a lot of nice methods there that SVD can use to analyze and do things. And what we can do is sort of try to combine the idea of Krylov methods to get efficiency for large scale problems with SVD type ideas to gain information about the problem. All right, so let me talk a little bit about this. So standard Krylov subspace solvers might do the following. So you, as I said before, you run a standard Krylov subspace method on it, and you truncate the iteration early. So I'm going to talk about various Krylov solvers in this talk, but I want to do it, if I can, in generality. So typically in a Krylov subspace solver, you would, of course, find a set of basis vectors, the V's and the U's, and you relate the matrix A between these basis vectors via another matrix. And I'll call it a T for a tiny matrix, but it could be, for example, a bidiagonal matrix. It could be tridiagonal. It could be Hessenberg. Right? So there are lots of different options depending on the Krylov subspace method that you use. And then typically what you do is you solve this projected least squares problem, the tiny problem, and then you project back to get your solution at the kth iteration. And when you do that, what you're doing is you're finding a solution, X, in a subspace. So it minimizes the residual in a particular subspace, and that subspace is growing as the iteration grows. And so the idea is that if this, of course, subspace grows, you get a better and better approximation to your solution. As I said before, if you truncate at a certain iteration, it mimics a TSVD-like solution. And so you stop the iteration when the solution is good enough. And there are, again, lots of papers on this, so I won't spend a lot of time talking about the history of this because it's so vast. But there are lots of great books where you can look for these sorts of things. And survey papers. So this last one is a survey, or more recent survey paper. All right, so I do want to mention something about, if you have all of these different methods, it'd be nice to have a codes to use. And so, Per Christian has his SVD packaged regularization tools. And he and Sylvia and I got together a few years ago and decided to put together a package that had iterative methods in it that could help solve more large-scale problems. All right, so let's try it out. I'm going to do a few Matlab examples in the beginning just to give you an idea of how these things work if you've not done these things before. So I'm going to use the standard conjugate gradient method on least squares problems to solve a particular problem. So let me just come over to my Matlab, and I set this up, and I'm going to run this real time. So it's a script that's running, but it's going to set up the problem and do things as I run. So in our package, we have a set of test problems. So this test problem is a seismic tomography test problem. So you don't need any inputs for it if you just want to set up a default test problem. And it will return a matrix A, a vector B that's not noise corrupted, and whatever the true solution it is. And then some information about the problem, not important. If you want to add noise to it, you can add noise to it. So I'll just do that. And let me just show you what the data looks like. So here's my measured data. As I said, it's a simulated seismic tomography problem. The true solution are these two plates colliding. And the idea is, given this data here, can you reconstruct that guy right there? And so let me just run the CGLS method. And so I'll just run it, right? So just give it A and B like you would a backslash kind of operator and see what it does. Now, of course, in an iterative method, I need to set up a default number of max iterations. I have stopping criteria in there as well, or we have stopping criterion as well. And then this, of course, it has to have a maximum number of iterations. Okay, well, so it stopped at a max number of iterations. And here's what the solution looks like. So in a way, not too bad, right? You can see, I think it looks much better than the original solution. But if you know these kinds of problems, you will notice that there's a lot of high frequency noise in here. Basically, what I've done is I've overfitted the data. And so what I can do here is to experiment a little bit because we have these codes to do this with. So I know the truth in this particular case. So I'm going to give the method the true solution and see what happened. So I just put it in as this option structure. It has the true solution in the option structure. Let me just run the same thing again and see what happens. And so basically, once I do that, because I know the truth, I can get the relative error at each iteration for this run, right? So then I can just plot it. So I just plot the relative errors at each iteration. So y-axis is relative error. This horizontal axis is the iteration. So you can see at about 20 iterations. So the error goes down about 20 iterations. It looks about where I've gotten my best solution in terms of relative error measure. At that point, the error goes up. Of course, the residual is continuing to go down. And so the residual doesn't tell me much about when to stop this solution. So if I could do the truth and find a good stopping place using the truth, that would be great. And if I did, I might get a less noise corrupted solution there. Okay, so that's just a basic run. And so you might say, well, how do you determine this good stopping criteria? And so this is where regularization parameter choice rules come in. And so probably the easiest one to apply in an iterative sense here is the discrepancy principle. So you would iterate until, instead of driving the residual to 0, drive it to about where the norm of the noise is. Often there's a little fudge factor put in here just to make sure things work. And our codes have these fudge factors incorporated into it. You can change them if you like. In any case, the idea is to drive the residual down to about the norm of the noise. Okay, so in our codes, you can set the noise level if you know it. I'll put it in here like this, and then put it in terms of my options, and see what happens. Okay, that's one way to do it. The other way is to say, well, you know, I sort of know something about my problem. Maybe I'll just solve the Tikhonov problem, and I know a good value of alpha. If I do, then I can run the same code by giving the regularization parameter, whatever the number is. I call it 20 here. I don't care what the number is. It's a regularization parameter for that alpha there. And I put it in and I run, and I get something that comes out. So let me just show you how these two things work. Just so you can see it in real time. And again, I'm running it real time. So I'm just going to set my noise level, run it again, and it stops. So it figured out that after a certain number of iterations, the solution reached about where the noise level is satisfied. And so you can see the solution is a lot less noise corrupted. And of course, these streaking artifacts in here, but that's hard to get out of these types of problems. And you can see where it stopped. It didn't stop exactly at the lowest level of error, but pretty darn close, pretty darn close. All right, so, and again, the other option is to say, well, I don't know the noise level, so let me put in a value for my regularization parameter and run it again. And if I do, it usually runs a lot more iterations because the error comes down and then sort of flattens out. And so it will run more iterations until it figures out a sort of residual tolerance to stop at. And if you do, you get a solution that looks quite similar to the discrepancy principle idea without Tikhonov regularization. All right, cool. So that's the basic idea there of those sorts of things. Now you might ask the question then, suppose I don't know the noise level and I don't know a good initial alpha, what can I do? And this is where you know, the work on what are called hybrid Krylov solvers come in. And so let's go back to the Krylov subspace idea again. So typically you're computing a set of basis vectors, you project the problem down to this tiny least squares problem, and then you project back. That's how the iterations go. And so you say, well, why not at this point, this tiny least squares problem, add a regularization to it. So I add regularization to that tiny problem, and then I project back that regularized solution, and I get a regularized solution at each iteration. Good. Well, this is kind of nice, actually, because if I do this, I actually have this least squares problem that looks like something that in the very beginning of the talk that I could exploit SVD on. And I can do that here because this problem is quite small. Right. So that's the idea. So I can apply SVD inside the iteration to these tiny problems, use generalized cross-validation or discrepancy principle to choose a regularization parameter. And then from that, also try to use the computed information at each iteration to determine when I should stop. If I know the noise, then we would use discrepancy. If I don't know the noise, we've implemented generalized cross-validation, but you could use any sort of regularization parameter choice guide here. All right, so our implementation, we call it a hybrid LSQR scheme because it really is like LSQR. It uses Golub-Kahan bidiagonalization. And it solves this problem here, as just as I said before, by projecting to the least squares problem, looking for a parameter there, and then projecting back. There's lots of nice work on this. Diane O'Leary and Simmons worked on this some years ago, and then Aki Bjork. And well, this paper, Bjork, Grimm, and Van Doren, I think is a very nice paper. So it was written in 1994, but it's a very nice idea of using these sorts of hybrid methods. And there are a variety of other papers as well. Our implementation is built on some work that Julian Chung and I did with Diane O'Leary some years ago, and is expanded on in a lot more detail in Julianne's PhD thesis. So that's the method that we implemented. There's also another implementation, I should say, Julianne has as well. It's a very nice implementation. So again, the idea here is to use the underlying Krylov subspace to help us find a regularization parameter as the iteration proceeds, and then determine a stopping criteria for it. And you can use it just like putting in an A and a B. You can put in other stuff if you know more information about your solution or your problem, I should say. Okay, so that's the idea. And I'm just going to do one more Matlab example because I don't want to spend too much time in Matlab, even though I find it quite fun. Let me just show you this, the LSQR example on this one test problem. So I run it. Again, all I'm giving it is A and B in this particular. Okay, so I didn't tell it the noise level. All I gave it was A and B. And so it by default uses generalized cross-validation to try to figure out a regularization parameter and to find a stopping criteria. The solution that I compute looks quite comparable to the Tikhonov solution that I had before. It's kind of interesting to see the regularization parameters. So at each iteration, if you, let me come back here. I hope this works here. So at each iteration, I need to try to compute a let me come back one more slide there. So I need to compute a regularization parameter at each iteration. So in the beginning, this tiny matrix doesn't really have a lot of information from which to do this. So what we do is we say, well, let's run it for a few iterations, say 3 or 4 iterations first, with the regularization parameter 0. Once this thing gets seeded with enough information, then we start using SVD and generalized cross-validation to try to find this alpha. So it's interesting to see how this alpha proceeds. So here's how it looks. Again, we don't start until about the 3rd iteration. And once we do, it finds a regularization parameter. And then as the iterations proceed, it starts to refine the regularization parameter as it goes, and eventually stabilizes at a particular value until it finds the stopping criteria at which to stop. It's nice. Now, I'm not going to claim, as with any method for inverse problems, that this is going to work for every single inverse problem, but it works quite well for many problems. All right, so there's my example. And then, so let me just say one other thing. So I did that with Golub-Kahan bidiagonalization. So I get an LSQR type method. It is also possible to do this with Arnoldi and get GMRAS-like methods. And so there's lots of really great work on this. The implementations that we have basically come from Sylvia's work with Paolo Novati and of course in her PhD thesis as well. So there's a lot of great work to see in these papers, all of these papers here. So let me pause here and see if there are any questions on this essentially introductory material.
I don't see. Okay, so there's a question. Let me just unmute Mohit. Okay. Can I do it like this? Okay, Mohit, I think you can go ahead with your question.
Okay, so yeah, hello everyone. So what I wanted to ask you is that instead of vector x in this problem, if we vary matrix A and x and b are fixed and we put some structure on A, like semi-definite structure, the same regularization technique will work, or what about, can we say about ill-posedness of the problem?
Yeah, it's a great question. So if X and B are known and A is not, it depends on the relationship between A and its unknown parameters. So A would depend on certain parameters, right? So if A depends on certain parameters in a linear way, you could rewrite it like a least squares problem so that the unknowns are not X, but whatever the parameters are that define A. Mostly, my experience is most often if A depends on unknown parameters, it does so in a nonlinear way. And so then you need to think about, so all of these methods are that I'm talking about apply to linear problems. So can you write the unknowns, that whether it's the solution X or the parameters that define A in a linear way? If you can't, then you need a nonlinear solver, and there are many, of course, options for that. And so if you say, for example, write it down as a regularized nonlinear least squares problem. So this piece here would be a nonlinear least squares part plus a regularization of the unknowns that define the matrix A. You can do it. In each iteration of the nonlinear scheme, you're going to have a linear system that typically that needs to be solved. In those cases, you can use some of our methods in the inner solves there.
All right. Okay.
Yeah. Okay, and Cleve Mola also had a question. Go ahead, Cleve.
Hi, Jim.
Hi, Cleve.
Are there any random numbers involved in what we've seen so far? If I run it again, would I get different results?
No, there are no random numbers in this. I don't think we have anything random in here. So the only randomness is in the noise of the right-hand side. So if I were to generate a test problem, so in my, let's see, I went, let me come back to my Matlab. When I run my test problem, I add noise to it. So that's random noise. And so if you're going to rerun it and you want to repeat exactly what you're doing, you should set the random number seed generator back to some number that you know.
Okay, thanks.
Okay, and Alex says there are no questions on YouTube, so I guess you can just continue for now.
Okay, thank you. So great questions. Let me come to other problems. So this is where we get to a little bit more recent work. So the idea here now is that I would like to solve, again, a fit to data term plus a regularization, but here it's not quadratic anymore. So applying direct Krylov solvers here is not so straightforward. There are lots of different ways, of course, to solve such a problem. There are many, this problem is not such an unknown thing in optimization community, but we were interested in what we might do in terms of Krylov methods. So first of all, one can, for such a problem like this, adopt an iteratively reweighted norm approach or an iteratively reweighted least squares approach, where you're going to replace this guy here with a 2 norm that approximates the 1 norm. And it has to be a weighted norm. So think about it like this. If I were to take vector x and I were to divide by 1 over square root of all of its entries, then I would get something in a 2 norm that looks like a 1 norm. Now, of course, I don't know the true solution, so I can't really apply that directly. I can't get that W, that ideal W matrix. But what you can do is do an iterative sort of scheme where you say, well, I'm going to take an initial guess x0. I'm going to compute weights based on that initial guess, and then solve a least squares problem with those weights. I get a new solution, and then do the same thing. Take the new solution, find new weights. And again, this is all done element-wise. So x is a vector here. K minus 1 is iteration. So I'm going to take the whole vector, square root every entry in it, do a dot divide to get this diagonal matrix. Okay, so basic idea is simple and not a new idea. So once you do that, then you can think about iteratively solving these least squares problems, these weighted least squares problems. And when you do that, now you can use any of the Krylov subspace methods that we did. Now, one nice thing about this approach is that you can transform to standard form. So you might ask, well, what happens if I have to divide by 0 here? The beauty of it is if you transform to what I might call standard form is that division there then goes away in some sense. All right, now we could also add a fudge factor here to just bump it away from 0 if it is 0, and that would be fine too. In any case, if you write it down in this sort of way, now you have what looks like in some sense like a preconditioned least squares problem, if you like, right? On the other hand, the preconditioner depends on the iteration. So you need to use a flexible Krylov type method for this kind of approach. And so here are some papers that discuss this a little bit. And I'm going to show you how we get to what we're doing here. So this idea is quite nice. And you can do it in terms of like a flexible GMRes or which is what we did in here. So it's generalized Arnoldi-Tikhonov. And then here is some more recent work by Julianne and Sylvia on Golub-Kahan type bidiagonalization approach. Oh, sorry. And we implemented this in our package. We call it IRL1. It actually really makes a call to this flexible GMRes, hybrid flexible GMRes scheme here. I won't show you the examples because I don't want to spend too much time on examples, but it works basically in the same way as all of the other codes. All right. The last bit of piece I want to talk about are low rank solutions. And so here's the idea here. This is the most recent work that we just finished. And it was basically motivated by lots of nice work in, say, stochastic differential equations that look for low rank solutions. And the idea there is, of course, to run a Krylov subspace method and to do some truncation during the iterations. And so we wanted to try to apply this to inverse problems and try to do it in a way that made sense to us. And so, so what we're going to try to do is enforce what we might call a Kronecker rank structure. So, so I'll talk a little bit about what that means. Basically, if I take this vector x and I reshape it into an array, so use Matlab's reshape function, and then think about this array here as a matrix and think about a low rank version of that guy right there, and then transform back and it gives me a Kronecker structure of the vector. Okay, so so our first implementation of this was to take this work, I cited this before by Julianne and Sylvia on the flexible Golub-Kahan bidiagonalization approach, and to use that scheme to do this. Now this is a nice extension of Golub-Kahan. Basically what it does is it computes two sets of orthonormal vectors and relates the matrices A and A transpose to two matrices M and T. And so in the standard Golub-Kahan bidiagonalization, of course, you have a bidiagonal matrix. Here you have these, these iteration-dependent, excuse me, vectors. And so then these matrices, you can't maintain bidiagonal structure anymore. So the matrix M is upper Hessenberg and T is upper triangular. And then you compute a projected solution, and then you basically project back. So that's the idea here. And again, you can do this sort of Tikhonov regularization in here, and then apply regularization parameter choice schemes in here as well. All right. So to maintain a low Kronecker rank or a low rank solution, you have to do some truncation. So you truncate parts of the things that you're doing. Now, you can take and truncate a vector, and then once you apply matrix A to it, you may lose the low rank structure of it, or the low rank structure tends to increase at each iteration. So this is why you often have to do truncation at each iteration. So the basic idea seemed to work well. And so what we did is we said, well, let's try to think about it in another way. So another way to think about it is in terms of nuclear norm regularization. So here what we're going to do is think about, forget about the truncation part. Let's just incorporate the low rank structure in terms of a regularization term. So what we're going to do here is use a nuclear norm on this, I'm calling it vec inverse. So just think about it as a reshape long vector X into an array. And so, and once you do that, then you can think about the singular values of that array, right? So I can compute the SVD of that array. And what I would like to do is sort of compute a solution that has sort of a low rank sum of these singular values. Right, so that's a nice idea. You can also generalize this into different P norms, if you like, P nuclear norms. So instead of just adding up the singular values, I might take a different value of P here. So something between 0 and 1. And so the insight, of course, is to try to maybe allow a little bit more singular value sparsity in there. So there are lots of methods that have worked on this kind of problem, and so I listed a few papers here that we used in our motivation, and so we decided to adopt this again iteratively reweighted norm approach because it was so closely related to the L1 approach that we were using, and we thought we could do that in terms of a Krylov subspace kind of idea. Right. So there's a lot of math in here, and I don't want to show it all because it would be rather boring to show all of the math in here. But what you can do is you can boil it down to, if you like, a fit to data term plus this weighted version of vector x, and there's a lot of stuff in here. So the v and the u are again an SVD of the solution x reshaped as an array, right? So if I have a million by a million, I reshape it into a 1000 maybe by 1000 array, take its SVD. So these matrices are not so big. This is a diagonal matrix, and there's this gamma parameter here that's added to it just to bump anything that's 0 away from 0. And this gamma actually turns out to be maybe important in proving optimality conditions, but in the numerics, actually, as I'll show, it really doesn't matter that much. All right, so I know this is a big mess in here, but just this is a Kronecker product. You have identity matrix, you have diagonal matrix, and you have another Kronecker product here. And of course, you don't form these things explicitly, you just do matvec mults with it. But this looks very much like the L1 approach that we had before. We have this weighted version of X. Right, so we can then solve this thing in an iteratively reweighted norm approach, where we solve this least squares problem, we adjust gamma, and then we solve it again. And so yeah, so we have an inner and outer iteration going on here. And so this guy in here would be solved maybe by a Krylov subspace method, if you like. We can then, the beauty of that, of course, is that you can then choose regularization parameters using the sort of Krylov solvers that we have. All right, so yeah, and the other thing to do is that you can, so let me come back to here. All of this stuff is on X. I can move it, transform to standard form by replacing X with this guy multiplied by X, call it X tilde, move this stuff over to here, and I get this sort of what you might call transform to standard form kind of idea. And again, it looks very much like what we had before. And so I have this this scheme here that looks like a linear least squares problem. I can hit it with a Krylov solver. I can have my Krylov solver help me choose lambda as I go and solve the problem in that way. All right, so we can do this in terms of either the Golub-Kahan bidiagonalization approach, so LSQR-like kind of method, or Arnaldi. So you can use a GMRes type method as well. So you need to update whatever the relevant factorizations are corresponding to whether you use bidiagonalization or Arnaldi. And then, of course, you're going to use those projected problems as you solve them to tune the regularization parameter as you go. And again, the idea here is that this gamma parameter should decrease. So you start off with a value of it, and then you repeat. Now we can put all of this into one Krylov solver. So this is an inner-outer iteration. And so we can put it all into a Krylov solver. And the idea here is, again, to think about it like flexible preconditioning again. So we put it all in terms of, let me come back to this guy here. Think about this as a flexible preconditioner. It changes at each iteration, and I update as I go. So that's what it would look like here. And again, this idea of using Krylov solvers to find the regularization parameter can easily be applied here. All right, so let me show you one example. Oh, I should say, yeah, let me come, this is sort of important, and the details are messy, and so I don't want to show it on a slide in this talk, but we're using this W and this S here, which are built from an SVD of, if you like, of my solution vector. I can use something else here, actually, if it means that it gives me effective, if it's effective at producing low rank solutions. So again, you're thinking about it like a flexible preconditioned least squares problem. If you know a particular set of matrices here that will help in this, you can do it. In fact, you can think about using the Krylov vectors. So you start your Krylov method, you start building up Krylov vectors. You can actually use the Krylov vectors to build these matrices instead of the solution itself. Now, that's going to be hard for me to explain in this talk, but we sort of describe it a bit in the paper here. But it can be effective as well. All right, so let me just show you one example since I'm running out of time, just to show you how it might work. So this is just a sort of, we applied some blur to the image, then we removed a bunch of pixels just to see what it would look like. A picture like this, you might expect if you did, so think about this as a matrix itself. If you do an SVD of it, you might expect because of all of these constant values in here that it should have low rank in itself. So we apply the low rank regularization to it. If we just apply standard LSQR to it, we get a solution that looks like this. And then here's just applying sort of the initial idea where we truncate the LSQR information at each iteration. That was our first try at it. And we got a solution that looked like that. It was better. But when we moved to the nuclear norm approach, it actually worked quite a lot better. And this V here corresponds to that variant. I said I could incorporate different kind of preconditioner in there rather than the standard that we did over here. In any case, the solution's pretty good, and we have in our paper a variety of other numerical experiments as well. All right, let me close just by saying that I really think these Krylov methods can be powerful for these large-scale inverse problems. It allows us to use adaptive guides to choosing regularization parameters. We can encode regularization through iteration-dependent preconditioning. This is a nice idea, and we've shown we can do it with various things, not just Tikhonov regularization, but L1 and nuclear norm. Our codes are in this package called IR tools. We implement not only these Krylov methods I talked about here, but a lot of other methods as well. They're not all things that we developed on our own, but we thought we should include a bunch of things that people wanted to experiment with, including things that have box constraints on your solutions as well. I should say, put a shout out for this Air Tools 2 it's a tomography package by Per Christian and Jakob Jorgensen. It's a very nice package. We actually linked to it. So rather than reinventing all of the stuff they did in there, we just combined the two packages together. So we tie into this for our tomography examples and some of the iterative methods that they have in there. And the package can be used in a variety of different ways. You're welcome to play with it. And if you want to, you can get it via the paper and the code on GitHub. And that's it. Thank you very much.
Thank you very much, Jim. Before I pass to Zoom chat, I would like to ask you a question. How do you choose the reshaping size in X?
Yeah.
Do you have a structure in the problem that you can exploit?
Yeah, it's a great question because so you take you have your vector X, you need to reshape it. Typically, in most of our problems, these X's correspond to images, and so they have a sort of natural ordering in terms of the reshape. But you're right, there might be an optimal reshape that gives you an optimal sparsity of the low rank structure in some sense. And that I don't know how to do. Given a vector X, what should be the optimal reshape?
Does it matter? I mean, experiment, did you see any difference in by changing the shape size?
We didn't try, actually. But I think it's an interesting question to ask.
Okay, so Jörg, just go ahead. Thank you.
Okay, I guess the next question is from Ilse Ibsen.
Hi, Jim. Great talk. Hi, Ilse.
I
just wanted to know, what is maybe you answered that already right now, what is the intuition behind a low rank version of a vector? But now you said that the vector was really at some point a matrix. You said an image. So deep down that vector was a matrix already, and by doing by reshaping it again as a matrix, you're getting a low rank version of the image. Is that it?
Yes, that's it, right? So think about it as a low rank version of the image, but you can also think about it as a separable structure of your vector, right? So take one vector, Kronecker product with another vector, Kronecker product with another vector, and so forth. How many do I need of those to add up to give me something that gives me the vector X? So think about it as a Kronecker rank in the vector sense. But if I reshape it into an array, then it becomes a rank in terms of the matrix sense.
Thank you.
Okay, and next question is from Rosemarie Renault. Go ahead,
hi,
I think.
That was great. Have you thought about, or maybe I'm not quite understanding how this works, if your data that you're trying to reconstruct comes from a 3D rather than a 2D formulation, in terms of this whole reshaping? I mean, of course, in 3D, you can think about you can reshape your 3D into a 1D vector and then do a reshape to 2D, I guess, for the SVD, but have you thought about this?
Yeah, it's a great question. We haven't implemented that. I think my personal opinion about it is some work that Misha Kilmer and I did some years ago, was to reshape it into a 3D cube, and then to think about the rank in terms of the sort of tensor rank of the cube then. But we didn't implement it. And as you know, the tensor rank then becomes a bit more dicey in the cube sense.
Yeah. Okay.
Okay, good. I don't see any more questions, and Alex writes no question on YouTube. So
okay, so
Cleve also has another question. So let's unmute Cleve. Okay, it should work.
Yeah.
Go ahead.
What about color images where you got RGB components like in JPEGs?
Yeah, I mean, I think most, so you can try to do it in terms of a 3D sense, but often people, I think about them in terms of just 2D problems in many cases. It depends on whether you have, interaction, cross-color interaction between the frames in some sense. If you do, then I think you have to think about it as Rosie suggested, is to do something like reshape it into a data cube that is, has three panes in one direction. But you could then think about then extending it instead of just RGB to multispectral and hyperspectral imaging that comes up in microscopy and things like that.
Okay, and then there's the next question by Christian Kümmerle. Go ahead.
So I was wondering how you choose this update parameter. So the update rule for your smoothing parameter gamma.
Yeah, gamma is so gamma is in some sense not a smoothing parameter, but more of a fudge factor to make sure this thing is not equal to 0 here. So that's a great question. So this gamma here actually turns out to be, and I should have mentioned this before, turns out to be something that may be critical, as I said, in improving optimality conditions, but in the computations, we found it not to be so critical. In fact, we in all of our test cases, we take it to be 10 to the minus 10 in the first, so initialize it to be 10 to the minus 10. And then we just divide by 2 in each case. So it's essentially 0. So it doesn't really have much effect on the solution. The big critical part is this lambda here that you need to get right. And that's where the Krylov solvers come in. This gamma is not such a big deal to us.
So, but this matrix WP gamma, or rather if you do your trick you showed, you rather have the inverse of it. It is then somehow ill-conditioned, right? Because if this gamma is very small, it should be ill-conditioned.
Yes. So yes. But you know, I think I don't know. I don't know how to explain it in a clear way. Basically, this term here doesn't really affect our computations. You know, we can actually even set it equal to 0 if we want to. And in our computations, that ill conditioning is not felt in the solution that we compute.
I see. Thank you.
Okay, the next question, excuse me, comes from Hiroshi Murakami. Go ahead.
I ask you how the behavior of your algorithm that regularize the solution changes if the precision of the floating point numbers you use are changed.
Good question. You know, I think, you know, as you know, right, so precision of floating point numbers depends on, you know, I'm trying to squeeze out a lot from something that may not be very precise. So in many cases, it might be just fine to use, say, single precision. I don't know about going all the way to half precision or something like that. But I think in most of these problems, single precision is perfectly fine. Now, if you're talking about mixed precision arithmetic, then it becomes very complicated. And I don't have an answer to that question right now.
So sometimes we may not obtain the good solution by the reason that the floating point precision is not sufficient. Am I correct?
Yeah. I mean, I'm not sure. I'm not sure I understand the question. So can you clarify?
Do you think sometimes we need higher precision even you regularize solution by these methods?
You mean, no, I don't think so. I don't think you need to go to higher precision for most of these problems.
Some problem may fail because of the precision of the floating point number are not sufficient.
Yes.
Okay.
Okay.
Okay. So I take over.
No, I think Vladimir Drushkin, is that a question?
Okay, good.
Yes.
Go ahead.
So nice talk, James. So question is, I mean, couple of questions. So first question is, have you tried like Sparse SVD, because especially for this L1 type of approaches?
Okay, so first of all, Sparse SVD. So you mean, what do you mean, SVD of the matrix A itself?
Well, I would say with sparsity constraint. You put sparsity constraint on SVD to make singular vectors look sparse.
Yeah, we haven't done that. You know, I feel it's hard to make the singular vectors sparse in many of these applications. I don't know an application where the singular vectors themselves are sparse.
I see. Okay. And second, I just want to bring attention because I think quite a lot of literature, I think early 2000s and maybe late 1990s in geophysics literature, they do this flexible like L1 approach. Basically, they do total variation. They use pretty similar things with, not of course with your reshaping, but with a variable norm,
Right. In fact, the work that we did here was motivated by some of that work, right? So there's work by Brent Wahlberg and some of his colleagues on using iteratively reweighted least squares types of approaches. But in those cases, you know, they don't really think about it as a flexible Krylov subspace method. They do it more like an inner-outer iteration. So you resolve the least squares problem each time this guy here changes.
Yeah, you're right. They don't think of that like that, basically. Okay.
Yeah.
Okay, thank you very much to everybody for this lively discussion. Yeah, go ahead, Valeria.
Okay, thank you very much,
Valeria,
James.
I should stop my screen share.
I think I'm doing it already. Okay, so thank you, everybody. Here is the program for the next 3 times. So we'll cover the whole of March. And we all hope we will join us. And thanks to Jim once again for his engaging talk. Bye-bye, see you soon.
Thank you, Valeria, bye-bye.
Bye.